Okay, we are back here discussing the big pulse, the triple pulse, and triple verse theory. We spoke about the pristine energy, which was the first energy that was expelled during the first pulse, which would form a force and a particle. We spoke about the photons and the gluons being similar because they are massless, they have no charge, and they have a spin of 1. This shows that the imprinted information will be imprinted in a similar energy zone. Not the same energy zone, but a similar energy zone. Right? We never spoke about the 3 pulses, which can be considered as 3 separate mini universes. Now, if we compare one of these pulses to the Big Bang, we will see that they have the same structure, meaning that they have an energy zone which pulsed, and we can consider that as a mini-verse, a mini-universe, one of the triple pulses. So we can say that, well, they're like 3 separate mini-universes. So we can call them mini-verses, right? We also, this will become important when in a few minutes I'm going to talk about Schrodinger's equation, right? Now we said particles are not stupid because they have information imprinted on them. We discussed that before. We discussed energy fields, energy levels, energy bands, and energy zones. We discussed generational particles, right? All these things we have discussed. Now, the Big Bang says that when the singularity banged, they had the one electromagnetic force that split into 2 forces, the electric force and the magnetic force. Right? So one has to ask, did the chicken come first or the egg came first, right? Because if we say electromagnetic force is considered the chicken, right, as the Big Bang is stating, then the 2 eggs would be electric field and a magnetic field. But the big pulse is saying, well, we had the magnetic energy field or zone pulse into the magnetic field or energy zone to create an electromagnetic energy zone, right? And these 2 zones sandwich a photon energy zone, which acts as a force carrier, right? A photon is, light, right? So this is what the big pulse is saying, contrary to what the Big Bang is saying, right? Because what the Big Bang is actually saying is that everything was in a soup, everything was all mixed up, right? And when the universe cooled, forces and particles were created, but they're not telling you which order. They just said everything was in a soup, and it cooled, and then this is what we had. But the big pulse is saying no, they were ordered during the energy levels, zones, and bands. There was order, but the Big Bang is saying differently, right? Similarly, the Big Bang is saying that quarks and anti-quarks were created during the Big Bang, and when it cooled, when the Big Bang cooled down, the quarks and anti-quarks appear, right? And if you were to take a quark out of a proton, because the protons make up of 2 up quarks, 1 down quarks, and is bound by the gluon, which is a particle carrying force to the strong nuclear force. So if you were to rip a gluon out of the proton, a quark out of the proton, right? Let me back up for a second. A quark cannot exist on its own. It cannot be a free particle. It has to exist in pair. A quark has to exist in a pair of a quark and an anti-quark, and that's what they call a meson. The particle now becomes a meson, right? It cannot be a free particle. But the Big Bang is saying that after the Big Bang, the energies cooled into a quark and an anti-quark, right? But the big pulse is saying that no, there was a meson field, a meson energy field that created a quark and anti-quark when it pulsed. Right? And I believe this is a more sensible explanation. Right? So the quark and the anti-quark would always have an interaction during one of the pulses, right? And it was created in a pristine energy field. So you have to think about that for a minute, right? So the meson was first an energy field or energy zone. Like we said, which came first, the chicken or the egg, right? The Big Bang is saying the chicken is the quark and the anti-quark, and the egg is the meson, right? That's what the Big Bang is saying. But the Big Pulse is saying no. We had a meson zone, which is the chicken, right? And when it pulsed, it created a quark and an anti-quark. This is why they can interact with each other. So the anti-quark does not come out of magic or the quantum vacuum to attach themselves to an anti-quark. No, the anti-quark, anyway, attach themselves to form a meson. Anyway, I really don't want to go too much into that, but next time we will discuss that. This is what I want to discuss. Schrodinger's equation. So the Big Pulse is saying, if you have a barrier, as best as I can explain it, say of sand, and then we have a wall, right? We have the sand and we have a wall. When we have a pulse, doesn't matter if it's a strong nuclear energy pulse or the weak pulse, weak energy force pulse, consider pulse. So it pulses this way and this way, and this zone, energy zone, interacts with this outside energy zone, and within the sand there's going to be an interaction here, right? There's going to be a mixing of two energy levels, two energy zones, right? One zone here, and then as it pushes it out, a strong barrier will be created here, right? Because remember, there's a force acting on it from the outside. A force, well, there were no forces, but an energy field, right? So far we have that. So if we were to expand this outwards, we can have the barrier sand with the wall here, which is an energy field, strong energy field, for example, and they can only expand so much, right? So we have a mixing here, which we will call, of course, an energy band. So we know, you have to have that, get that right. So we have the energy bands. So when we pulse outwards and we hit this barrier here, we're going to have chaos, all kind of chaos, right? We're pulsing outwards, see? Pulsing outwards, right? Pretty much a uniform pulse. And then when we hit this energy zone, we're going to have all kind of chaos. Then when it pulses back in, right, we have chaos. Then we have a smoother continuous zone. Then we hit this barrier here again, well, the barrier, right? here, right? We can have chaos again. We have a lot of chaos, right? But then when it pulls back, so between the chaos here, we can have a continuous smoothing out of that energy level. Until we hit this barrier, then we have chaos. So when we hit this barrier here, this is where the spin is imprinted, right? The spin is intrinsic angular momentum. So you come in here with one momentum, you hit the barrier, this is when the spin, which is the intrinsic angular momentum, will be imprinted in this energy level, field, and the fluxes which is the DNA of the particles, right? And if we were to, I'm just showing you the walls that it will hit. But if we were to make it spherical, right, we can see where the pulse is going to hit, the barrier is going to be here, and stuff like that. Now, here's an important thing. We're talking about the Schrodinger equation. Previously, I had said there are too many probabilities in the mathematics of quantum mechanics, right? And as before, I stated particles are not stupid. They have information imprinted on them, onto them, like the spin, the charges, and the masses, right? So Schrodinger's equation, I can't remember what it is, but it's something like it defines a wave function, right? I think it's I h bar equal psi h bar psi h, something like that, right? Equal. So this defines Schrodinger's equation, right? But Schrodinger's equation does not work for every instance that we observe empirically, right? When we do the experiments, it varies. So why do we have that variation? Because of what I just drew and explained, right? When we have the energy fields expanding or contracting, we're going to have a smooth distribution of the field. But when it hits the barrier that it cannot go forward along, it's going to be chaos. When it goes back, this chaos is going to smooth out again. And it hits another barrier this way or this way, we're going to have chaos. So what this is trying to explain is that we can have the probabilities in this chaotic section of the field, right, where it hits energy barrier. The strong energy barrier can go forward, but they are going to be mixing. So the Schrodinger equation deals with probabilities. So the Schrodinger equation should only deal with this section of the energy field, the wave function, and in between here, we need another equation to explain what's happening here, in between here, where the energy field will be more continuous, fluid, and kind of constant. But the Schrodinger equation only explains a general equation. We need a more specific equation to explain the particle movements, the momentum, and the position. So we would have to have Schrodinger's equation plus the equation here, a continuous equation. It's called the middle equation, plus the chaotic equation here in this direction. Schrodinger equation, this direction. Schrodinger's equation in this direction. Right? So we have three equations. And if it will, this is one pulse. Then when it pulses inward, we have to have another Schrodinger equation going this way, right? Plus a middle equation plus the chaotic equation from here, right? So chaotic, kind of not too chaotic, and a chaotic equation here, right? So we can have one equation this way, one equation this way, and another. We have about 3 Schrodinger's equation to explain specifically what is going on in our universe, because we're dealing with these energy fields and fluxes and bands, right? And this is what, when it cools down, it creates the particles, the different particles, and so on and so forth. So that Schrodinger's equation has to be expanded, probably like a series. And when we see the empirical evidence from the experiments, we adjust our formulas to suit what we see. So they would, come up with all kinds of equations. They're going to add, they're going to tweak the equations to fit what they see. Because Schrodinger's equation does not explain everything in the universe. Schrodinger's wave function does not explain that. And this is what they call renormalization, right? The equation does not fit every instance, but they renormalize it by tweaking it. But now we can clearly see that the equation needs a lot more work. We have chaos, we have kind of a normality in one direction, so be it in this direction, right? So we're going to have a set of equations instead of one Schrodinger equation. And you're going to say, well, how does this take us further? Now we have the double slit experiment, right? And the double slit experiment we all know about. But if we have an electron, say for example here, in this diagram, right? We have an electron here, right? So in this diagram, right? In this chaotic part of the diagram, right? This is all chaos. When the field slams into the stronger another energy field, right? There's going to be chaos here. So we have an electron here. Now we can put in the Schrodinger's equation for this probability, right? Because of all the chaos. But when we go in this direction or in the middle of here, right? The particle is going to be in a wave-like situation. But as it progresses to a normality of the leveling of the fields, we can see exactly where that particle is now going to be defined, right? So the particle can travel in a wave, in a kind of a wave, but it's still a particle, and it can be defined actually in the middle of the energy bands, right? So when we start out with an electron shooting it through a slit, it's actually chaotic, it's actually wave-like. But when we observe it as a particle because of the imprint that has been, embedded into that particle. So when we create an electron is actually chaotic from the imprint, right? And as it moves along and we measure it actually, you can see it's a particle. This is why the double slit experiment is giving us this information, right? So we can define a wave function from the big pulse theory. We can explain the double slit experiment from the big pulse theory, right? What else can we do? We can say whatever's chaotic over here is not the same as the chaos here, right? So we have to define every point of the pulses, right? Not just using one equation. There's a set of parameters, right? Here to here with chaos, and then when we have a little smoothness, and then we have more chaos, and then we have the spin, right? So that can be defined. And there's quite a few things that can be defined, right? And I just spoke about renormalization. I heard this recently, a physicist says quarks are weird things. But quarks are only weird things if you do not understand it. Right? We delve in way back in this theory before the Big Bang. In fact, the triple verse, the triple pulse, can be considered as the inflation cosmology theory. Right? We have the pulse, the universe expanded rapidly, exponentially, right? And the big pulse as the Big Bang. But in between, we have different pulses. So I think that's it for me. So in the future, if I'm not clear about Schrodinger's equation, superposition, and I'll go over it again, and we have to understand that although we have electrons, and we say the mass of the electron is whatever, right? It does not mean that all electrons have this mass, right? Not all elementary particles would have the same mass. Electrons could be a little bigger in mass or smaller in mass. But we do not have that realization, right? Because we don't have the measurement capacity to measure every electron. So the electron can have a higher mass than what we told, or a lower mass. And next time we take that into consideration, right? Because if the electron have a higher mass, then we can say it have a high energy, right? Because of c squared. That's how fast it can travel, you know. See, you cannot travel faster than the speed of light. Right. So we have to consider the electron mass. And if we can measure an electron, the mass of it, you know, the mass, and to the 1,000 degree, a million degree of accuracy, still the electron is not going to have the same mass as another electron. Something that we have to consider, the masses. All right. So think about the Schrodinger equation. We can have 6 sets of equations. You know, vector, you know, going in different directions, different wave functions, and we have to put them together to really solve what's going on with quantum physics. All right, thank you. See you next time.